All right, so as discussed in one of our lectures on conservation of energy, we have the idea of a system where we compress, push an object down on a spring, and then we let that object launch and it flies up the air to a certain height. Of course, we got that exact concept here. We have a ball that sits inside and you push it down by a certain amount. I don't know if you can see the color change, but based on how far down this thing goes, it's now been pushed down relative to its initial starting height, and then if I can lower it enough, it launches up to a certain height. And presumably hits that height, and then we know what that height was. So we can take and, for this apparatus, we can see that it can actually be compressed to 3 different lengths. So there's 1 level, 2 levels, 3 levels, with, of course, the most compression corresponding to the most stored amount of energy. So, with that in mind, what we can do is, if you go back to the lecture where we went through the derivation, you see where we came up with the formulas relating the amount of stored gravitational potential energy, the amount of stored spring potential energy, and came up with an expression for how high it went based on how much it was compressed, where D represents how much it was compressed, and H represents how high it was ultimately launched to. Well, it turns out that, as we often do in lab, we can rearrange this expression to solve for an unknown quantity that we want to have. In this case, the thing we don't know about this setup is, what is its spring constant? Clearly there's a spring in it. That spring must have a spring constant. So if we take our conservation of energy equation and we put certain measurable quantities on one side and certain measurable quantities on the other side, then we can again find ourselves in a situation where, hey, if all of these are values that we can determine, we can directly measure height and how much we've compressed something, we put all those as, say, one of our variables, and we take that distance, we compressed it squared divided by 2, and that just has that form because of how the equation looked. Then this entire thing here becomes our another variable. So that means if we were to plot this out, this y variable, all that as a function of some x variable, then ideally, because we expect the spring constant to be a constant, then it's going to form a straight line when we plot that. And in this case, the slope of this line would be whatever the spring constant is for the spring. So I sat and shot the ball up by 3 different times based on compressing it down to its 3 different settings. So in compressing it 3.5 centimeters, it's able to launch relative to its starting this height here, relative to this point. It launched up by 53.5 centimeters. And then, the next tick down was basically compressing by 5.5 centimeters. And so here you can see the different numbers associated with this. Now, these values here are not what we need in order to plot, because we want to plot this whole set of quantities as a function of this. So what you're going to do is you're going to, as part of your lab, you have to get access to some sort of spreadsheet program. Either Google Sheets or OpenOffice, or as a student or someone associated with an education role, you should have access to like Microsoft's online, Excel and all that stuff. But part of your lab is going to get access to that. Then you're going to make me a spreadsheet, and you're going to put this table in it. Then you're going to put this table in it with calculating these values, so d squared over 2 and m times g, h plus d, where those values are given, and where you'll have that plot, or sorry, you'll have that chart. Note that when you're doing this calculation for these cells here, make sure you use g equals 9.8 meters per second squared, and the mass of that yellow ball turns out to be roughly 10 grams. So, but we're going to put it in kilograms. That'll make the next step easier. We're using those, put in those numbers, then you have to make the plot. You have to make the scatter plot. Then you have to put in the trend line. then you have to interpret that trend line to give me the size of the spring constant of this. You'll also note, if we plot these values as a function of this and these data points appear to form a roughly straight line, then we know the spring constant is constant as we expect. If you plot the data and you find that it doesn't form a straight line, then that'll just tell us that there's other things going on in here, and this spring might be away from its sort of equilibrium in the sense that it might be way overly stretched, or when it was designed, it was put under a lot of tension, so it just it's harder to pull. But I just checked it, and it should form a straight line, and so we should be able to have a measurable spring constant from this. All right? Then, just to double check that you have gotten the spring constant in the correct units, one of the things you'll calculate for me is you'll use this expression here, and you'll find, assuming that how far this is pushed down isn't fixed by these little notches, and we could compress it to an arbitrary amount, you'll calculate the distance that you would press the spring such that, or basically what is the minimum distance you would have to push that particular spring, pointing off screen. How far would you have to compress this in order to actually get the thing to launch? The minimum distance. And as discussed in the lecture thing, that satisfies this formula. And so these values, right? G is 9.8, M is 0.01 kilograms. K here, if you have K in the right units, then when you solve for D and convert D into centimeters, you'll be able to give me a value. So I'll know whether or not your units are correct just based on whether or not you're basically off by a factor of 100. So that's all that's the main work for this lab. Note, you'll also see on Blackboard there's going to be a question there where here, as I also discussed in the lecture, I showed how we could have this formula where we could know the height the thing will launch to based on how far we've compressed it. And because this has the form of a quadratic formula, we can turn this equation around and say, hey, if I want to launch to a certain height, h, how far do I have to compress the spring? Notice with this formula, we can do the same thing. But in this case, I can ask, if I want to have a certain launch velocity, how far would I have to compress this? So you're going to have to take this formula here. You're going to have to solve the quadratic equation. So you're going to get d equals, but this time in terms of some in terms of the velocity term. You're going to use the spring because it's going to be in Blackboard, it's going to have a spring constant there for you. So there's going to be a stated spring constant and a stated mass, and you're just going to have to solve, like in this case, how far would I have to compress this thing if I wanted a desired output velocity, right? So you may have to brush up on your quadratic equation stuff if you can't solve this. But hopefully at this point we've done enough quadratic equations. You should know how to take and sort of unpack this kind of thing, get some nice expression, and then just plug in and solve for the desired quantity. All right, so so most of these labs, because I'll be just sort of like doing the sort of data and laying out stuff for you, so it'll be up to you to take, again, find the software you need, put together, generally you'll just put together an Excel sheet, and if you need some data analysis, I'll just tell you what to put in there. But this time, really, all you have to give me is show me you can create a chart, you can create another chart, you can create a plot that's a scatter plot, you can put in the trend line, and can read a piece of information off that trend line, and then do a little calculation. Right? So that's all I need for this first lab here.